We've already discussed how scientists use position to compare ages of different rock layers. The lower the layer of the rock, the older it is. Geologists try to match similar rock layers in different locations to see if they were formed at the same time or under similar conditions. Using color, texture, and composition, scientists try to match rocks. But the same rock types are not always the same age. It's more helpful to match the sequence. Sometimes, though, even the sequence may be the same, but the layers weren't formed at the same time. To further complicate things, rock outcrops may be found separated by a wide distance. While one outcrop shows layers from a geologic period, the other outcrops represent a different time. Can we put these pieces back together to complete the story? Solving this problem involves correlating information, and that's the main idea of this video. Correlations show that rocks or geological events from different places are the same or similar in age. Fossils are probably the most important way to correlate different layers of rock that are separated. Rock layers can be identified by the fossils they contain. Fossils are the remains or evidence of former living things. Fossils are typically found in sedimentary rocks because igneous and metamorphic rocks would destroy the organic remains. The fossilization process is unique. In order for fossilization to take place, an organism must be buried and then compacted beneath layers of sediment over time. As this continues, the animals or the organism's minerals that are in the bone are removed by water in the ground. They're replaced by minerals that are present in that particular region. The mineralization process changes the bone to rock. As uplift occurs, it brings this fossil to the surface and uncovers it. The reason why fossilization is so unique is because of the specific environment and the specific steps involved. Only 1% of life on Earth has been fossilized. The Earth has had life on it for about 3 billion years, so 1% is a very small amount. Fossil succession is an example of how fossils can be used to estimate the age of rock layers. Notice how all these rock layers contain fossils, but there's a definite progression from the fossils that are found in the lowest layer to the fossils that are found in the upper layer. Fossil succession shows a first to last appearance, and in other circumstances that certain fossils appear in groups together. Every fossil tells us something about the age of the rock it's found in, but index fossils tell us the most information. On our reference tables on page 8 and 9, down on the bottom of the Geologic History of New York State, there are 23 different index fossils. Each index fossil is represented in the reference table by a letter. Those letters correlate with specific geologic time periods, as well as important geologic events in New York State and the world. It's these index fossils that allow us to correlate events that have taken place across the Earth. Index fossils have to have two important characteristics. The first characteristic is that the organism that made the fossil has to have lived over a wide geographic area. The other characteristic is that the organism has to have lived for a relatively short amount of time. This is Mantis, which lived in the Middle Devonian for approximately 10 million years. I know that seems like a long time, but for other organisms at that time, that was relatively short. So with index fossils, scientists can make connections between distant rock layers and their ages, connecting locations that were seemingly not related to one another. To determine if a fossil would fit the criteria to be an index fossil, we need to evaluate those two criteria. So let's try to determine if one of these four fossils, fossil A, B, C, or D, would be an index fossil. We'll start with fossil A. Did it live for a relatively short period of time? The answer here would be yes. I know that because it's only found in layer D and none of the other vertical layers going up. The next question would be, did it live over a wide geographic area? Well, according to this map and these layers, the answer would be no. It's only found in one of the 3 zones or outcrops shown. So fossil A cannot be an index fossil. Let's evaluate fossil B. Fossil B is located here, and the first question is, did it live for a relatively short period of time? Well, in this circumstance, because it's found in multiple vertical layers, that would be no. It does not fit that criteria. The other question is, did it live over a wide geographic area? The answer for that question is yes. It is found in all 3 locations, so that shows a wide geographic distribution. Moving on to fossil C. Now, fossil C is located in layer C, and the first question would be, did it live for a relatively short period of time? Yes. It's only in one layer. And did it live over a wide geographic distribution in this circumstance? Yes, it did. It's found in each outcrop. So this fossil, fossil C, fits the criteria to be an index fossil and can be used to connect these three locations. And to finish with fossil D does not show that it lived for a relatively short period of time. It looks like it lived for a very long period of time because it's found in multiple vertical layers, and it was geographically distributed over all 3 spaces, so that would be a yes. So once again, only fossil C showed the 2 characteristics necessary to be an index fossil. There are other examples that can be used to correlate different rock layers. Those could be similarities in rocks. As previously stated, just because rock layers are the same doesn't mean they were once connected. But if we could match up those layers, they can help us determine what's missing. So in this circumstance, these 3 locations show different sedimentary layers and missing pieces that have been weathered and eroded. So using the similarities between the rocks, we were able to connect these locations. We can also use volcanic ash. When a volcano erupts, the ash and smoke are distributed rapidly over large areas, and this material is visible in rock layers. So here's some evidence of a volcanic eruption. That layer of ash material represents a volcanic eruption that took place, and it rapidly distributed that material over the Earth's surface. Other locations that contain the same layer and the same thickness of ash would match up into the same time period as this layer. Along the same lines, when meteorites hit the Earth, or large asteroids hit the Earth, they leave behind craters, dust, and layers of iridium that's also, similar to ash, distributed over the Earth's surface. Iridium is not currently or not often found on Earth. Iridium is usually delivered to Earth by meteorites. So since it's a rare Earth element, when we find it, it's a good indicator that at that time the Earth was hit with some kind of space object. And just like with volcanic ash, when we can match up layers of iridium with other locations, we can assume that those were from the same exact time period. So that's how we use different pieces of data to correlate rock layers. That's it for now. Thanks for watching.